Hey guys, welcome to Conceptual Geometry, lesson 4.1. Today we're going to talk about line, point, and rotational symmetry. First, let's start with line symmetry. Line symmetry is, we'll call it a fold line. You have to fold the object in half. So imagine if this object was cut out of a piece of paper, could you fold that such that one half of it would fold exactly on top of the other half? In some of these cases, I think it's going to be kind of easy. In others, it might be a little bit more challenging. First off, here we have, it should be marked, an isosceles triangle. So I'm hoping you guys can visualize, if we were to fold right here, this half of the triangle would fold over and lie exactly on the other half. So yes, this does have line symmetry, and that would be a line right down the middle. So all you have to do is sketch that in. Next, we've got a rectangle. Again, I think it's pretty obvious that if you were to fold like this half of the shape would fold over to the other half. So it's got a line of symmetry right here. But that's not the only way you could fold that in half. What if we folded it this way? So then this half would fold down onto that. So there's also a horizontal line of symmetry. Next, we've got like this horseshoe-looking thing. Again, I think it's pretty obvious. We have a horizontal line of symmetry. Then we've got this weird sort of banner. What happens is it's not what we say symmetrical. So there's no way I can fold this and get one side to be like the other. So no matter what, we're going to have kind of an awkward shape. So here, there's none. And if there's no lines of symmetry, you just write none. Okay, let's move on to a rhombus. I know it's a rhombus because all four sides are marked congruent. And I think it's pretty obvious to see here, if you were to fold on the diagonal, this bottom half would fold exactly on top of the other. So there is a line of symmetry this way. And there'd also be one this way. Now we're talking about letters and words. The letter A is very similar to an isosceles triangle. So you'd have a vertical line of symmetry. The word book, it's not the letters individually, it's the entire word. So if you look at the B, the O, the K, I think you could fold it down the middle horizontally, and this bottom half here would fold exactly on top of the other. Okay, the word noon, that one's a little bit tricky. The ends are what's challenging. So I think if I do this, it's kind of obvious to see that the ends wouldn't work that way, but what about this? So this end would go over here and it would look like that. So no, it's not going to work. The word noon doesn't have any lines of symmetry. This one, oho, has one between the two H's and also a horizontal. So you'd sketch two of those in. Next, we have a parallelogram. Parallelograms are tricky, but I think you can see there's no way you could fold it. Because if I were to do that, this half here would actually go something like that. So that wouldn't work. If I try and do this, that half there would kind of look something like that. That's not going to work. So parallelogram has none, no lines of symmetry. All right, so I think that's the easiest thing we'll do today. Now it gets a little bit more challenging. Point symmetry. Point symmetry is if a shape has symmetry after a point reflection. That's kind of hard to visualize. So another way you can test point symmetry is if the object is the same upside down. Is the object the same upside down? So what I'm going to do here is I'm going to trace a few of these. Some of them are going to be easy and others are going to be a little bit more challenging. So let's go back to our rhombus. Let me trace this. And now watch me rotate it upside down. Is it the same shape? Yes. So we're going to say that it has point symmetry. Yes. All I have to do is say yes or no. I think it's pretty obvious a rectangle. If you turn that upside down, that's going to be the same. And I think the letter A is pretty obvious. If you turn an A upside down, it's going to look like that. It doesn't line up. So I would say this would be definitely no. Again, here's one that's a little bit challenging, the word cis. Now, you guys have the advantage at home. You can actually take your paper and turn it upside down and see if it's the same word. Give me a second to do that here. So let me rotate this upside down, and it's still the word cis. So yes, that has point symmetry. Tat, pretty obvious to me, those T's and the A, nothing would work if that was upside down, so that's a no. The word noon, again, I gotta think about it. Rotate your paper and see if noon is the same upside down. See if it's still noon or if those ends are backwards. Okay, let me rotate this. Yeah, check it out. Noon upside down is still the word noon. So yes, that has point symmetry. Obviously here, square, rectangle, yes, point symmetry. Parallelogram, challenging. Let me trace this and rotate mine upside down. You do the same with your paper. Rotating this upside down, check it out, still the same parallelogram, so that would be yes, point symmetry. So again, point symmetry is when the object is the same when it's upside down. Real easy to test, you just rotate your paper, your note packet, and see if it's the same object. All right, the final type of symmetry today is called rotational symmetry. Rotational symmetry is if you can rotate the object any number of degrees and have it be the same thing. So let me trace this first shape, which is a pentagon, and see if I can rotate it so that the vertices match up. I think you can see it's going to work. So this would have to go there, that one goes here, so on and so forth. Okay, so it might not be perfect, but if I rotate that, you're gonna see right here, it's the same exact shape. So now, that's how rotational symmetry works, but we also have to determine the degree of rotational symmetry. How many degrees do we rotate to go from here to here? So one thing that I hope is obvious, that if I rotate it all the way around to here, that's going to be 360 degrees. So rotational symmetry, you're able to rotate the object, but it has to be less than 360 degrees. Because everything is going to be the same when you rotate it 360. So what you do now to find that degree of rotational symmetry is you take 360 and you divide it by the number of points, if you will, that that object has. So this has 5 points. That means I'm going to take 360 divided by 5, and that will give me 72 degrees. So visually, here's what's happening. This angle right here is 72 degrees. And as the smallest angle, you can rotate that and have it be the same shape. Okay, now we have a parallelogram. Does it have rotational symmetry? Well, give me a second to trace that. You can start rotating your paper to see if it's the same. Okay, so now I'll start rotating. No, 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 yes. So this does have rotational symmetry, so the answer is yes. What was the degree? Well, if you turn it upside down, that's just 180 degrees. So again, I think it's kind of obvious. Certain shapes like a square, a parallelogram, a rectangle will be sort of obvious. The other ones are going to be a little bit more challenging. How about a circle? Well, that's kind of interesting, right? If you take a circle and you start rotating it, it's the same. Every single rotation is going to be the same. So all of those. So the answer is yes. The degree of rotational symmetry, I'm going to say 1 degree. It's actually, there's an infinite number because you could slice that up however many times you want. But we'll just say 1 degree. To the nearest degree, 1 degree. Next is an equilateral triangle. Again, this should be marked. But I need to figure out the degree of rotational symmetry to go from here to here. So basically, this angle. We'll follow the same procedure we did up above for the pentagon. I'm going to take 360 degrees divided by 3, so that has 120 degrees of rotational symmetry. Next, our star. What we have to do is we have to rotate it so this point of the star goes to that point right there. So I need this angle. Well, let's count how many points this particular star has. 1, 2, 3, 4, 5, 6. So I want 360 divided by 6. That's going to be 60 degrees of rotational symmetry. Okay, our next shape, we've got like this butterfly looking thing. And one thing we have to determine, are all of these the same size? And yes, they are. This would be a different scenario if like these top two were smaller and then the bottom two were bigger. It would still have rotational, oh no, that wouldn't have rotational symmetry, would it? So yes, they have to all be the same, and they are. So how many degrees do we have to rotate this piece till it goes to that piece? Well, we've got 4 of them, so we're going to take 360 degrees divided by 4, and that will be 90 degrees. So this has 90 degrees of rotational symmetry. And it's a little bit easier with these regular polygons. Basically, it's the same concept as what we had up above. You just have to count the number of sides and divide by that many. So since this is an equilateral triangle here, it would be 360 divided by 3. We already did this one, 120. A square would be 360 divided by 4, so that would be 90 degrees of rotational symmetry, meaning you have to rotate it 90 degrees to go from here to here. That right there is a right angle. This is a hexagon. It's got 6 sides or 6 vertices, so that'd be 360 degrees divided by 6, or 60 degrees of rotational symmetry. So this angle right here is 60 degrees. And then, let's see, what does this have? 1, 2, 3, 4, 5, 6, 7, 8. That's going to be 360 degrees divided by 8. So that has 45 degrees of rotational symmetry, which means this angle right here is 45 degrees. All right, let's wrap it up here with some practice problems. We're going to test all 3 things: line symmetry, point symmetry, and then finally rotational symmetry. So remember, line symmetry right here, this would be a fold. Can you fold it in half? Point symmetry, is it the same upside down? And rotational symmetry would be any angle less than 360. Okay, the first one, the word un. Is there any way you could fold that exactly in half? No. Is un the same upside down? No. Is there any way we could rotate it to be the same? No. So this has nothing, none. The word zoo. Okay, can you fold that in half? I don't think so, because if you try doing this, that looks like it would not be, wouldn't match up with the one below it. So it doesn't have a fold. If you rotate it upside down, it's not zoo anymore, it's ooze. So nothing there either. No rotational symmetry, no point symmetry. The letter M. I think it's pretty obvious. You can fold that right down the middle. So we just sketch in that line of symmetry. And then it's got no rotational and no point symmetry. Because if you start rotating it, it doesn't stay in M. Okay, how about H? I think it's pretty obvious here. You can fold an H vertically. You can also fold an H horizontally. Can you turn H upside down and have it be the same letter? Yeah, it's still an H, so it has point symmetry and has rotational symmetry of 180 degrees, because there's no other angle you can rotate that and have it be an H except upside down. So if it has point symmetry, it'll definitely have rotational symmetry of 180 degrees. There might be an angle less than that. The letter B, depending on how it's drawn, this one looks like the top and the bottom are equal size. Has a horizontal line of symmetry, no rotational, and no point symmetry. Okay, next we got this goofy looking shape here, but it looks like I could fold that horizontally. So sketch in that horizontal line of symmetry. But again, I can't rotate it any amount. If I rotate it upside down, it's gonna kind of look like this. The point would be here. That's not the same shape, and any other, this will just be pointing somewhere else. So there is no rotational symmetry. So no rotational and no point. Circle. All right, right now I want you to sketch in all the lines of symmetry while I do it here. All right, follow along. Sketch them all in at home in your notes. Go ahead. Make sure you get them all. Keep going. All right, you get the idea. There's an infinite number of them, right? Let's just sketch in a couple. Too many. So yes, it's got line symmetry. It has point symmetry. Yes to point, and it has rotational symmetry, and we'll call it 1 degree again. We just did this one on the other page. Okay, these two hearts that are touching at the point, you can definitely fold this in half horizontally, and you can also fold this in half vertically, like so. Is it the same upside down? Yes. So it's got point symmetry, and then it also has rotational symmetry of 180 degrees. There's no other angle you can rotate it to be the same until you're upside down, so that would be 180 degrees. Okay, next we've got this modified plus sign with these arrows on the end. You can definitely fold this in half horizontally like so, and vertically like so. But the other thing that's important to see here is you can also go diagonal and diagonal this way. So this has 4 lines of symmetry. It also has point symmetry. Is it the same upside down? Yeah, it is. So it's got point symmetry. And it also has rotational symmetry equal to 90 degrees, because notice this has 4 points, so I do 360 divided by 4. Basically, this has the same rotational symmetry properties as a square. So that would just be 90 degrees. Okay, we got a hard one here. Looks like a sun. So in terms of lines of symmetry, we can go through point to point. So we have to sketch them all in. There's a finite number on this, so it's not unlimited like a circle. But you see here it gets a little tricky because those aren't the only lines of symmetry. Not only could you go through point to point, but you could also go between them. So there's 4 more. Here, 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 and here. So those are all the lines of symmetry. It definitely has point symmetry, because if it's upside down, it's going to be the same. And one way to test that, if you fold it, would this point match up with that point upside down? And yes, it does. And then rotational symmetry. Wow, let's see, how many of these are there? 1, 2, 3, 4, 5, 6, 7, 8. So for my rotational symmetry, I have to do 360 divided by 8, which is 45. Rotational symmetry is going to be 45 degrees. And then our last shape right here. Again, I don't know what to call this, but can you fold it in half? Yep, you could fold it right here horizontally. And looks like you can fold it vertically. Is it the same upside down? Certainly is, so it definitely has point symmetry. Is there any angle other than 180 that would work? No, this has to rotate all the way down there. So it does have rotational symmetry, but it's 180 degrees. Okay, so that wraps up day 1, something a little bit different. You guys haven't done this before. This whole unit will be a little bit different. It's called transformations. We're going to be taking objects and rotating them and flipping them and translating them and dilating them. So it's kind of a new unit. Please reach out if you have any questions whatsoever. Feel free. You are now prepared to do Delta Math Homework 4.1, and we'll see you guys in class soon.